Thanks for that. Yes, this does seem loud. If it's loud, we can turn it down. So I made it so that you could actually follow along the slides as I talk, which I think for some of the younger students they may enjoy it. So you can get it there and also go to this short URL. But anyway, the slides will also be provided after. So the title of my talk is Capturing Noise in Single Trial ERP Analysis Using Simple Decompositions in Neurocognitive Modeling. So I'm going to start out talking about really a simple technique in order to find some single trial potentials that you can use in your own research. And then I'll talk about some modeling that we're doing that I also think is helpful in capturing the noise in EEG. So let's start off with like a guiding experiment. This is an experiment that we're doing in the lab again, but also something I collected at the University of California, Irvine. So say you first on an experimental trial see visual noise, something that looks like an old TV that's out of service, so it's changing fuzzy noise. And on top of that changing fuzzy noise, you see a Gabor patch or a sinusoidal grating, and it's just a simple two-alternative force choice. So you press one button if it's low spatial frequency, and that's just a larger number of bars and fatter bars in a defined area, or press another button if it's high spatial frequency, thinner and smaller number of bars. Yeah, and the participants learn this over the period of the task. Well, of course, we could collect traditional event-related potentials to this onset, the onset of a Gabor. I think everybody's familiar with event-related potentials, so I probably don't have to talk about them. But the other speakers have mentioned this, but the problem with event-related potentials is that we don't really see them on single trials. So first I'm going to start with a simulation of EEG, a simulation that has noise in it, and I'll just look at the first trial and show you that you can indeed see anything. So this is the noisy simulation. So what I'm simulating here is just activation in the parietal cortex. I chose the superior parietal lobule because that seemed reasonable. It's centered in a way at this of the label of the superior parietal lobule, and then it has a 10 centimeters extent in folded space. This is just the average from an average brain from free surfer. This is just the activation, so I'm looking at the back of the brain here, just the two areas of activation. And then what I'm simulating here is just a dampening sinusoid, which you can see on the right. And so, yeah, this is the only thing that this brain is generating besides noise, and so I should be able to see this in an event-related potential. That's exactly what I see. On the left is just M&E's event-related potential default plotting software. I see certain peaks over parietal electrodes, and yeah, I can see this kind of dampening sinusoid. This is kind of like a poor man's ERP, right? And then now this is the first trial and multiple electrodes. I just kind of chose some central electrodes, but also electrodes where I expect the peak. So CP1, CP2, P1, P2. And then this is all these channels on the first trial, and there's no obvious dampening sinusoid. In fact, the amplitude on the left looks about the same as the amplitude on the right. So there's, it's noisy, right? So this is going to be a driving simulation, and I'll come back to it when I talk about the simple method to detect single trial ERPs. Of course, EEG is noisy. I can move through this quick because I'm talking to an EEG audience. But yeah, I mean, why would you expect noise in EEG? Well, there's a lot of outside artifact, of course. Eye blinks and eye movements, EMG from the jaw, actual changes in electrode impedance because the the electrical contact has changed when you move your head. Not only the EMG, but the actual electrical artifact from that movement. yeah, 50 hertz noise, EKG, and then some bodily movements that is actually pervasive in EEG as well. And this could actually be, even though I have a typing here, it could actually be tonic EMG that's affecting the EEG. So it could be there's no actual movements, you're just activating your muscles in your body, and that's shot through the skin to the skin of the scalp. And for those of you, I didn't put a citation here, but for those of you that don't know the study of Fitzgibbon et al. And John Willoughby, who are in Adelaide, Australia, they literally paralyzed participants. They barely paralyzed briefly themselves with this agent and showed how after 20 hertz, a lot of the power of the EEG spectrum basically goes down to near, in the paralyzed EEG, the power spectrum goes to near zero, which means that a lot of most power above 20 hertz is driven by tonic artifact. And so that's to say that we can do a lot of artifact cleaning procedures, but we still expect a lot of tonic artifact in EEG. So this is not like obvious EMG that you can extract with ICA. This is tonic power in the EEG. And of course, there's other cognitive sources. You're all familiar with ICA, so I can kind of blast through this. I just put this up as there are other cognitive sources. So not only do we have artifact sources when we run our ICA, but we have multiple components that we think is actually driving brain signal. So that's to say that, so this becomes now important on single trials, because on single trials, well, we expect there to be multiple cognitive potentials, potentially, in single trial EEG. Okay, so then how can we, if in this noisy reality, how can we find these single trial ERP estimates? So I'll talk about one example question that I really focused on in about 2018, which is a question related to decision making. Romeo also already talked about some models of decision making and value-based decision making. I was really interested in perceptual decision making. Luckily, I didn't chose not to study the CPP. Luckily. But let's just split a time of decision into 3 different time periods. The time that you, if you come to this traffic light, right, and you have to decide to stop or go. And who would decide to stop? And who would decide to go? And who would kind of slow down and roll through the stoplight? Yeah. Yeah. Yes, I don't know the correct answer to this, but I like this example. Yeah, I think that third option is probably what I would do. Anyway, when this is in your visual field, it takes some time for you to recognize that stimulus is actually there. And that's a time period that I'll talk about now. And of course, there's also time to make the decision itself and time to execute that decision. Yeah, these are kind of three broad times. Maybe there's some other times. Maybe there's some parallelization here. But I'll just split it like that. But there's other reason to suspect that at least if there's some parallel timing here in decision making or in the motor preparation, that there should be actually a sequential period before you actually make a decision. And that's because, well, at the very least, there should be like a 40 millisecond delay, because that's the time it takes for visual information from the eye to reach visual cortex. 40 to 60 milliseconds or so. There's some evidence, though, that it should be around 150 milliseconds. I'm going to not talk about that, but I have an example slide. But this example question is, well, with EEG, can we actually measure that period of time before a decision before a decision starts? Okay, so to do this on single trials, you could use a simple decomposition. And this simple decomposition that we found is really useful for the potentials that we're interested in, these early visual potentials, is essentially just principal component analysis on the traditional ERP data, but then you apply the weights to the single trials. So where I'm getting the scalp map is from the ERP data. So if I go back to the first slide, the ERP slide. So this, if I think about this data as a matrix where I have time as my rows and my columns are the electrode space, if I just take a principal component of that, do principal component analysis on that matrix, then I get now a decomposition with components as my columns and time as my rows. I'm just going to take the component with the highest amount of variance in the data, so I'm taking my first component, and then what I have now is a weight over channels that gives me that first component. Okay? So when I do this, I have these this weight over electrodes, and I just apply these weights now to the single trial data. So this is one single trial of EEG. It's filtered EEG in this example. And then I'm just applying these weights, and now I get a better estimate of my single trial event-related potential, right? So it's just a property basically of doing this weight averaging over where I think the ERP should be, and then finding that weight average. Essentially, this is what you're doing with ICA and any decomposition that finds weights over channels. So yeah, you could replace it with any decomposition here, but I think this is one of the simplest decompositions you could do in order to improve your signal-to-noise ratio on a single trial. Yeah, and it's just a few lines of code, so I encourage you to look at the Python script here. It's really just a simple decomposition. So yeah, if you want something quick and dirty, I mean, this is the solution. Okay, now going back to the simulation. So yeah, well, I just simulated the data. I took that simulated EEG data. I took the PCA of the ERP. This is my weight for the first component. It explains about 50% of the data. Yeah, that's pretty high because the rest of the data was noise, but sometimes that is actually also true in real data. And now this is all the trials of the EEG in this component, and I can obviously see this dampening sinusoid. Yes, it's still noisy, but I've really improved my signal-to-noise ratio. Yeah, so a really simple point, but I think oftentimes a simple decomposition is useful. There's probably things that outperform. You could also take this and do some deconvolution in the time. This doesn't do any deconvolution in time, right? But this is something to get much better a signal-to-noise ratio if you have high-density EEG. Now we've kind of advanced the methods in some way. Well, in 2022, my PhD student Amin applied this to multiple participants in a really noisy data set where the EEG was just not recorded well. I think this, if I remember correctly, I think this was also simultaneous fMRI, but I can't remember now. But anyway, you can apply this technique to multiple participants and get their specific scalp map in order to estimate, in this case, we're just calling it an N200, so a peak around 200 milliseconds. And you can see that, well, depending on how the cap is positioned, depending on the orientation of their brain inside their skull, we'll get different scalp maps for different participants, so you can really make this specific to the participant. I will say that there's varying degrees of success depending on the recording. So some of these we really think we're estimating quite well, like this one. These red bars are latencies at the boundary. So this is just a distribution of the latencies of this N200 over trials. And some of these are pretty well, yeah, it's obvious that we're kind of capturing those latencies pretty well, because if we're finding the minimum at the boundary of our window, then we kind of think, well, that's not a good estimate. Also, it seems that if we extend our window, then there's reason to suspect that we're not really capturing that latency. It just seems that some trials don't have enough SNR to really estimate that single trial N200. Whether or not that means that it's actually there or not is maybe an open question. But yeah, this is just to say that, well, this technique was working better for some participants than others. In this paper, we also do a bit of modeling to deal with the edge effects. So that's kind of one advancement, I guess, is that you can do this on multiple participants. But what we're working on now, or not really working on, but what we've done with my now PhD student and then master's student is that you can put it through an automatic pipeline, so you don't have to choose the component. You can just template match it based on averages. So if you're interested in a specific waveform, the single trial N200, you can just put it through a template match, and then you kind of automatically get that component that you need. So if it doesn't map to the first component in your PCA, right, you can just do a template match. I will say, though, on single trials, if you have a lot of variability, so another master's student, Ximing, is looking at a data set that we recorded where we're inducing a ton of variability into the N200. And that template match, in that case, doesn't work so well because in time, this waveform really varies on where it peaks in time. So yeah, in that case, you would just use the scalp map. Okay, so now getting back to the driving experimental question, can we estimate the period of time before a decision is made? This goes back to my 2019 neuroimage paper. This is just showing now the actual components, these are just PCA components in multiple participants in multiple experimental sessions. But now there's there's 6 different experimental conditions. There's 2 experiments with different types of visual noise, and then the contrast of that noise changes, making the task more difficult. And so when the noise is has a really high contrast, it pushes that N200 much later, and it also pushes response time much later, which was a key finding. So this is just to show that we have a ton of variability in this N200 actually across. Well, this is on an average, but also on single trials, driven a lot by the feature of the noise. Okay, so like a really simple analysis that we did is that, well, if this N200 really is tracking the onset of decision making, then if we throw all of our trials in, and it was about 17,000 or something trials, just collapsed across everything, right? Collapsed across conditions, participants, and sessions, experimental sessions. We should have a beta of 1. So if the N200 latency is our predictor variable and our response time is our dependent variable, then the beta coefficient should be about 1, meaning that a 1 millisecond change in an N200 should describe a 1 millisecond change in response time. Of course, we expect noise in this linear regression, and that's obvious, but if we have enough data, then we should be able to well estimate that beta coefficient. And so this dotted line here is the hypothesis, a beta of 1, and you can't see it so well on this particular PowerPoint, but the true regression line here is a black line right under that line, and also our confidence of that line is really high, so there's also a 95% credible interval around that line, and it's very shallow. So of course, for those who are familiar with linear regression, the R squared here is abysmally small, right? And that's because the variance is really high, but our estimate of the beta we're very sure about that beta, and that's what we care about here. Well, why is the variance so high? Well, if we estimated the single trial N200 perfectly, right, which there's reason to believe we didn't, but if we estimated the single trial N200 perfectly, in decision-making theory, we know that a ton of variance in a response time is due to the decision-making process and not just the time that it takes to start the decision-making process. So it's wholly expected that we have a ton of variance here. Yeah.
Have you looked into amplitude as well?
Yes. So the amplitude is also predictive of the different cognitive parameters. But here we didn't want to put amplitude into the regression, and that's because we fully expect that amplitude and the latency are tied. but we want to keep it on the same millisecond scale. So if a question is the latency if that latency describes the onset of decision making, but then the amplitude is, let's say it's completely correlated with latency, well then it'll be this bouncing beta problem where it's depending on the noise in the data, you can have an effect on the amplitude or the latency if they're highly correlated. So we want here actually to not put that variable in. So it is true, it is going to be a correlated variable, and it will change this regression a lot. But there's not a good reason as to why to put it in when they're highly correlated. So it's kind of, it's,
Oh, I didn't mean to correct
yeah,
for it, but
yeah.
I want to say that in a very different task,
Yeah.
I found that into amplitude predicts response time.
Yes, so,
In a detection type task.
yeah.
So I was just wondering if you've looked at that also.
Yeah, so we did, so the paper that came before this, the 2017 mathematical psychology paper, we also look at amplitude, and yes, it does predict non-decision time. It also predicts actually the evidence accumulation itself. In this particular paper, we're trying to get at the question of can we actually track timing in EEG? And so it's a more appropriate regression here. Okay, so any questions about kind of simple decomposition? This was really kind of like it's partly displaying research, but it's kind of also saying, oh, well, look at the script and play around with it yourself. Yeah.
Regarding simple decomposition,
Yeah.
compared it to like a super simple decomposition where you kind of drag a box around those central electrodes in let's say the damping sinusoid.
Yeah, so if you drew a box, these weights are kind of optimally found to be descriptive of the average, the ERP average. So drawing a box, in some sense, would not, it would be worse kind of on a theoretical level. But if you just averaged a few electrodes together, if you found the right electrodes, it would definitely be better than looking at single electrodes. Yeah, so yes, you could do that. I mean, that would be an even simpler decomposition. Yeah. So if you have a strong enough signal, then yeah, just averaging together electrodes also makes sense. Okay. So now I'll move on to neurocognitive modeling, which is really, is really kind of my area of expertise and something that I'm trying to advance in the methods level. So Romy talked about a theory of evidence accumulation. Does anybody, probably also a lot of people study decision making here. Maybe I'll go through it quickly just in case. Maybe there's someone in the room. But on a neurocognitive theory is if this N200 is truly tracking the onset of evidence accumulation, what would this look like graphically? Well, if you are, this is like the psychological construct of cognitive evidence, right? That's somewhere in the brain or aggregated and nowhere in the brain, but just the psychological construct of collecting evidence to make a decision. In a simple drift diffusion model, you start the evidence accumulation at some point after the stimulus onset, so after that Gabor onset. And then if you have enough evidence for a certain response, let's say pressing the blue button, this is operationalized as you pass a boundary. So that boundary is a level of relative evidence, and as soon as you cross that level of relative evidence over time, then you make that choice. So this is a classic drift diffusion model. So I'm collecting evidence over time. Time is the x-axis, right? And as soon as I have enough evidence, I make a decision. It's as simple as that. But it's relative evidence. So if it's evidence against the blue response, then you would make, you would press the yellow button here. But key to this theory is that it's also describing this N200 latency, the onset of this evidence accumulation. And so, if I simulated multiple trials, it would look something like this, where the latency is changing based on the start of the evidence accumulation over trials and also have different evidence accumulations per trial. And so I'm collecting now all my response times and all my choices, but I'm also collecting now all my N200 latencies on single trials. This is just another way to look at it. This is one trial evidence accumulation. This is all trials of my N200, and I expect that there's some variance in this, what we call visual encoding time, but it's just time before a decision starts. That variance is described by the variance in the N200 latencies. Just another way to look at it, but also to show that, oh, well, it's clear that this component is just encoding the N200 and then otherwise is noisy. You also, this not really relevant for this talk, but you would expect a period of time after the decision to make a motor response. This is the classic idea in evidence accumulation theory, is some fixed time, and usually what you can estimate is the sum of the encoding plus the motor time, which is called non-decision time. Okay, so now this is from a neurocognitive model that we did in the original 2019 paper, where we're just looking at embedded regression. So we're fitting this drift diffusion model in a Bayesian way, but we have an embedded regression where the N200 latency is a predictor then of the non-decision time, which is the sum of encoding and motor response. And in this theory, a 1 millisecond change in the N200 latency should correspond to a 1 millisecond change in non-decision time. This is a trial average response. I'm actually questioning why I put this figure in here. Anyway, we found some evidence for the trial average response, and this is because, well, we expect high evidence around this blue line. In Bayes factor, we found some moderate evidence for an effect of 1. It's clearly above 0, but we were more interested in this strong hypothesis of beta of 1. And also telling is that when we estimate the residual non-decision time after accounting for this N200 effect, that it seems to be similar across conditions. This is more qualitative because there's not a test here. But qualitatively, doesn't seem the effective condition, even though it really changed the estimates of non-decision time when you fit it just in a behavioral model. You can reduce the variance from the task when you use the N200, and then there's this kind of fixed delay for the rest of non-decision time, which we expect is the motor response. Now, what we did not find is a single trial relationship. So this is just like a traditional event-related potential, although it's kind of like the PCA version of the traditional event-related potential as an input into the model, as like a dependent variable into the model. We also looked at a deep independent variable on a single trial level, and that one, while the beta coefficient was positive, and we have a lot of evidence for positive, we didn't find any evidence that it was equal to 1. So that was kind of evidence against the hypothesis. I don't know why I didn't include that figure here, but that's what it is. But now a problem with that kind of analysis is that you treat a noisy measure as an independent variable. And in regression analysis, when you do regression, what you're actually assuming is that the noise is only on the y-axis. You assume no noise on the x-axis, and you assume only noise on the y-axis. It's just a property of regression. In practice, we usually have independent variables that we think are noisy in some way, but that's not what you're telling the model. You're telling the model that noise is only on the y-axis. And it has some implications, because in models where you assume that there's noise on both the x and the y-axis, you get slightly different results in regression. It's kind of similar to this error in variables idea, and there's a different kind of regression, basically, where you have noise in both the x and y-axis. However, it's hard to estimate, and that's why we don't use it. So what I could do is, well, I want to, formally define this theory with including the N200, but now I want to predict, instead of using this as an independent variable, I want to predict the N200 latencies from the model itself. And how to do this? Well, I have some simple mathematical statements, but I'll break it down for you. So the top one is just predicting the response time and the choice on a single trial I from a drift diffusion model. That's all this means here. It's just a drift diffusion model with certain variables. A boundary parameter, which is not important here, but then visual encoding time that we expect changes trial to trial, indexed by trial I, plus a motor time. This is the traditional motor non-decision time. So this sum is traditional non-decision time, but the total non-decision time is now changing per trial. The drift rate and the bias, which Romy mentioned, but I'm not going to talk about. So this is just a DDM. But now what's key here is that we have also a normal distribution where we have embedded in the normal distribution is something that changes by trial. So this is the single trial visual encoding time. So it's not something that we can observe, but something that we're assuming exists in the model. And now another key here is that the EEG on a single trial is not only due to the variance in that visual encoding time, but it's due to any other variance, which is sigma squared. And so this is like the noise term, which is literally any cognition or anything that's not descriptive of visual encoding time. And then just something to model the fact that there's trial-to-trial variance in visual encoding time. That's just the last statement here. I assume it's from a normal distribution. But a key here is that there's some variance related to cognition or some variance in visual encoding time. That's this S squared here. And this variance is part of the variance in my N200 response. And the other part of variance is just all other variance. So the total, if I measure the total variance of my single trial EEG, like I just take my var in Python or MATLAB, after I estimate my single trial latencies, then the sum of S squared plus sigma squared will always equal that variance. So one key feature now is I can actually find out, well, what percentage of variance is related to my cognition of interest in this kind of model. And this is really falling out from the fact that I'm now treating the EEG not as an independent variable, as a dependent variable, and also modeling the noise. And I think this is really a key aspect of EEG that we don't usually think about because we're often treating it as an independent variable in regression analysis, or we're treating it as a dependent variable and then having something that should also have noise as an independent variable. But now I'm treating both as dependent variables, both the behavior and the EEG. Okay, this is part of a general trend to model both brain and behavior. So if you think about Z as being all kind of single trial ERPs and X being the behavior or choice RTs in this particular example, well then what I'm really doing is I have some parameter that changes per trial, and that describes the trial level single trial EEG and the trial level behavior data. These type of models are quite hard to fit, and that's because you have this joint likelihood for those who are familiar with modeling, and it's not easy to solve these joint likelihoods because you have this kind of joint data, especially when this is changing per trial. So there's similar models where this doesn't change per trial, like you could just have a gamma here. It's a parameter that, let's say, a drift rate that doesn't change per trial, right? Or a visual encoding time that doesn't change per trial. But the problem with those models is that I could randomly permute my the trial index of my EEG and keep my choice behavior the same, and I would get the same predictions for the parameters. So it's not really tied data, and it would be more easy to fool those models into showing that something's there. Well, this model is really getting at more what we want, which is that, well, we expect, we're seeing if it's truly that a longer RT should also be associated with a longer N200 latency. Oh yeah, so the circle is, this is the key, is that this changes per trial. This is another key to these models, is this is not easy to observe, so we're not actually trying to estimate this trial-to-trial parameter. We're just assuming that it's there and then estimating the model. So if I just plot the same equations and I then put these circles just to show you how this operationalizes for this particular model, yes, I have behavioral data that's changing per trial. I have the EEG changing per trial here, and then I have the unobserved, but assuming it's there, the single trial parameter. And so this kind of, these three circles, these three nodes are something that we use in a lot of models, and we think this is kind of like a general framework. We have to estimate it using something, because we don't have a true likelihood model, we have to estimate it using artificial neural networks. I can answer the question here if there is one, but essentially this is a nice package, and this is also really easy to use. This team has some really nice examples. I have some of my own examples. Email me if you want an example. This package is really easy to use, and it's kind of up and coming. It's growing, and yeah, I'm really excited about it. I've had quite a few students use it with some success. So this is just estimating kind of any model that you could define in simulation. So I'm defining this model only in simulation, and then I do this where I train it on a bunch of data, a bunch of simulated data, and then I apply it to real data. So any model you can define in simulation, well, theoretically, you would be able to fit it. Yeah, this model works. This is the point of this slide. On the x-axis is the true parameter. On the y-axis is the posterior distribution. So the orange line is perfect recovery, meaning that my model is working. I'm getting estimates that are near the truth, or orange line is it's the exact estimate that is the truth. This is a Bayesian analysis, so I have some uncertainty with my posterior distributions. The blue lines here are the 95% credible intervals. Teal lines, or the mint lines, are the 99% credible intervals. My circles and my stars are my median and mean, respectively. This is just kind of a plot I like to show recovery. So this is really quite good recovery for a Bayesian analysis, just to show it works. And also I'm well estimating my noise in my EEG, and I'm well estimating the, in this case, the non-decision time variability. So this is the amount of variability in my single trial EEG measure due to cognition, and this is the amount due to everything else, right? And so what I can also do is just put this in equations. So now this is the proportion of cognition in my single trial EEG. And I don't have the plot here for some reason, but I also estimate this R well. That's the point here. Because I'm estimating the S and the sigma well, I can also estimate R. So what I can do is I can fit this model and then get estimates of R, how much variance in the EEG is explained by cognition. What was the point of this one? Oh, okay. I can also extend this model by putting a gamma here. So I kind of directly assumed that the EEG mean should be visual encoding time. So I'm kind of not testing my hypothesis. This is a better model to test my hypothesis. So I put one more parameter here, a gamma parameter. So the theory suggests that this gamma parameter should be 1, right? It's like my beta parameter when this was an independent variable, when the EEG was an independent variable. So now I'm going to look at this gamma parameter and see if it's 1. That's if the N200 truly tracks on a single trial the onset of evidence accumulation, gamma should be 1. And also R should be, if there's not that much noise, R should be pretty high, right? The proportion of cognitive variance. So these are results. Gamma is not 1 in this particular data set. That's okay, because I was more interested in the methods here than I was in the results. But at least I think this is like the best test of this theory, right? Is this model. So gamma in this particular data set, gamma is not 1. And also my R, well, for some participants it's kind of high, and for other participants it's lower, which I think is kind of expected based on some slides ago that, well, it seemed like we were well estimating the N200 on some participants, but not others. So you can also, you could also apply, to each individual and get these estimates for each individual. Yeah. Okay, so in summary, for the neurocognitive modeling, I put is helpful for dealing with single trial noise. I realized when I made this slide, I'm yet to have a comparison of all these things, and it's something that Amon's actually working on in a new paper, just to compare when it's an independent variable, how do we misestimate things versus when it's a dependent variable. Yeah, that comparison still needs to be done. I have a suspicion, though, that these models are actually the best method when there's noise. If there's no noise in the EEG, then yeah, the regression would be fine, or the embedded regression would be fine. Okay. Any questions about the neurocognitive modeling, or maybe questions from before? Yeah.
So I don't fully understand where that base flow model or method comes in.
Yeah.
As long as you're able to write down the model, would you be able to do something also like Markov chain Monte Carlo?
No, it doesn't work in Markov chain Monte Carlo, and it's more of a technical reason. The technical reason is that in Markov chain Monte Carlo, it's difficult to deploy Markov chain Monte Carlo without trying to estimate this on every trial. So in Markov chain Monte Carlo, I would have to estimate this parameter on every trial. And I could employ, it is a Bayesian analysis that has some prior, so you could find a Markov chain that would actually fit this model. But in practice, what we have to do for whenever we have something that changes on a trial level and we don't want to estimate it, we have to integrate it out. But now we have an integral of this thing, this joint distribution of these two distributions, and that's not easy to solve. Yeah, so it's a technical reason more than kind of a fundamental reason, like it's not defined. Yeah, there's some models that are less defined than this, but it's more of a technical reason, is that it's what we're trying to do is not estimate this lower one.
Related to two different sources of noise, the two nested Gaussians, like the sigma squared and s squared, or is it?
It would, even if this went away, if you fix this, you still have the same fundamental problem. Yeah. 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 Yeah.
I have a question also related to that. And maybe you weren't making a strong point there, but so you said like if you can simulate it, you can fit it. And I think that the new HDM is using a similar approach, right? Like the neural network.
Oh yeah, it does. Yes. Yeah.
And so Alex was presenting an evaluation of that approach early in 2019 or something, and then his poster was like, yeah, but you know, you still need like diagnostic data basically to be able to identify certain parameters, for example, like be able to properly estimate them, even with the neural network, and you still have issues like, you know, confusability, and you still have issues with parameter recovery if the model itself isn't, that you're trying to fit, isn't good. So
Yes, exactly. Yeah. Yes, it still applies. So it doesn't solve the fundamental problem of unidentified model. So this model is identified, meaning that if we have, as long as we have any behavioral data, which is response time and choice, and single trial EEG data, then this particular model is identified because there's only a few number of parameters for the amount of data points that we have. That's a simplification, but it's kind of like more like there's only a few parameters for the type of data we have. But in general, it doesn't solve the problem of unidentifiability. So let's say that we put in a simulation of the entire brain and we allowed EEG to be generated by single dipoles, extended cortical activations, kind of like in my simulation, multiple dipoles, and then you're simulating to the scalp. Now that problem is classically unidentifiable, meaning that you can't solve that problem without making some assumptions like single dipoles. So if you put that into Bayes flow and you allow it to have multiple dipoles anywhere, then you would have this unidentified model. And what it would reduce to is it actually might, so there's a difference between an unidentified model and model convergence. It may converge. So the model would be uncertain between multiple parameters. So there'd be this joint posterior space that's not like shrinking to a certain area. It's just, it's like, it kind of looks like a prior, right? So where was I going with this? Yes, so it doesn't solve the problem of unidentifiability, and that's something you do have to check. And it becomes even more important sometimes in this kind of method because you're simulating something and no one's ever fit it before, so it can easily be an unidentified model and you don't know. And I faced this in my own research. But now for model convergence, it tends to converge for the type of evidence accumulation models that I've fooled around with. I'm now looking into EEG models, so that remains to be seen. But there's tons of classes of models that they've achieved convergence for. So it's generally convergent even for unidentified models. Yeah. Yeah, but yes, you still also have to assess convergence. There's different ways of assessing convergence with neural networks in general that are helpful here, and they're different from MCMC, assessing MCMC convergence. Yes. Okay. So I have a couple of minutes now. My remaining talk is like, look what else my lab is doing. Oh, I will say that. Oh no, actually, I'll talk about this briefly. So we, Amin and I also wrote this paper, which is this idea of having this parameter that changes in a single trial that describes both behavior and EEG data. It's a general integrative neurocognitive modeling framework to jointly describe EEG and decision making in single trials. And we fit like a different combination of ideas, which is the N200 tracks visual encoding, the CPP slope tracks evidence accumulation. We actually have real data in this where we find a beta coefficient of 0, by the way, although it depended a little bit on how we estimated the CPP. So this is to say this paper is like a general, it's trying to present the general idea of using EEG as a dependent variable along with behavior. But we fit a ton of different models from this tree. And this is, the one integrative single trial framework to rule them all. So it's kind of a general principle of having behavior, EEG, and then having some parameter that changes on single trials that describes both. Okay. So I could talk about other things since I have about 10 minutes. My lab's doing other things. So 2 labs were mentioned. It's because I'm in the mathematical psychology group at the University of Amsterdam, and we call that the lab, which is the Amsterdam Mathematical Psychology Lab. And that's with Dora Matska and Andrew Heathcote, and among others, just everybody that does mathematical psychology and the psychological methods. And then there's my lab, which is the Mathematical Cognitive Neuroscience Lab, which is kind of a group of students that's doing things that I find interesting. So this is that lab. And by the way, there's a general tutorial to a lot of neurocognitive modeling, and we wrote this so that it would be useful, and Chiante is a PhD student now at UCLA and also helped me write this, make a nice R package for this, but there's also a Python package, and this is just kind of general principles if you want to do neurocognitive modeling of MEG or EEG data and behavior. Now I will skip to this because I kind of want to talk about it. Okay, so the other thing you can do in this kind of single trial integrative framework is that you could actually estimate cognitive parameters that you couldn't estimate before. Because you have additional data, now what used to be an unidentified model can become identified. When you find that one of an EEG measures is predictive of a parameter. So it's kind of a general principle. If I have more different types of data, that models start to become identified. Like if I observed the brain, if I knew that there were single dipoles, then yeah, the problem of EEG, brain to EEG on the scalp becomes identified, right? So it's kind of a general principle, although applied to cognitive modeling. In this case, the cognitive signal in decision making is the drift rate, right? So it's how well you do at the task. It's often modeled as like a measure of ability across multiple tasks. But then there's also a measure of the noise in the process, which is something that's always fixed because you can never estimate it with just behavior alone. So the within trial noise, this is the cognitive noise of evidence accumulation. And then there's the boundary parameter, which is the kind of the strategic parameter. You could push that boundary down and be faster and less accurate. You could push it up and be accurate and slower. These three parameters are classically unidentified. If you double two of the parameters, then if you double all three of the parameters, then you get the exact same prediction of choice RTs. So yeah, that means that we can't identify them if we try to estimate all three. So usually what happens is this one is fixed to 1. So in all packages you've ever deployed in DDMs, this is fixed to 1. But the key here is that we use the single trial integrative framework in a particular model, and we assume that the only thing that we assume is that the boundary could be related to some external data. We're thinking EEG data. And in that case, if it truly is related, then we can start to identify all three parameters. And only if it's truly related. If it's not related, then we just collapse to this unidentified framework, and we can tell from the model that it's unidentified. So I'm pretty excited about this. It exists as a preprint that's been submitted. This is kind of a less of an EEG paper, but the idea was to apply it to neurocognitive modeling. I will say that actually finding things that have enough signal-to-noise ratio so you could estimate that is still a pretty hard problem, but maybe something with a lot of data we could do in the future. And the idea is that a deeper reason behind this is we're interested in measuring individual differences in cognitive abilities, and we want to be able to separate cognitive signal versus cognitive noise. And so this is like a way that we think we can do this. If there are any questions about this, maybe email me, but read the paper first. Subtitles. What have I done? How did this happen? Okay. One thing I'm also very excited about is that we have, with my student Maria, we're building models of EEG that are just global models. A global model of EEG is something that assumes that the frequency dynamics and other dynamics of EEG are just due to, in this case, axon propagation delays and no local behavior. Usually a global model is embedded in a local system, so there's both local oscillators and global connections or long-range connections. But you can actually drive a lot of the dynamics in observed EEG, like the alpha rhythm, just from global dynamics. So if we have distributions of delays between brain areas, we can actually create an alpha rhythm. So I want to mention it to this group because it's still pretty new, but Maria has a talk in mathematical psychology that is going to be released on YouTube pretty soon because there's a virtual math psych coming up, where we show that, you can actually use like a simple autoregressive model. You embed anatomically informed axon distribution delays, and then you can start to generate algorithm. I've also used in the past to generate event-related potentials. And these are like truly global models where all the local activity is just noise, and then the information, that noisy information is just being sent through the brain with certain delays from a distribution. Yeah.
Is the whole result of that model generated by basically bottom-up activity?
It's just bottom-up activity where we assume it's literally, in this case, pink noise. So it's just at every, it's kind of a broad area, and at every area, let's say some parietal area, and in every area it's just noise locally, but that noise is being sent to another area, and then you start to generate an algorithm. As long as there's connection back and forth, basically. Yeah. There's feedback loops, but not a local feedback loop, but a long-range feedback loop. Yeah, yeah. So it does, there is an oscillation, but it's a long-range oscillation. Yeah. Yeah, well, this is, there's some more impressive results now. This is but we have some issue with the low frequencies, but anyway, you can generate an algorithm, which is what we're excited about. Maria has a much better talk than this one. And then finally, I will say this, with my PhD student, Chris, he's looking at basically embeddings and large language models and looking at how when a large language model can perform a analogical reasoning task, so these puzzles here, right? Both humans and LLMs can perform them. Seeing if that LLM then is a model of the brain. So looking at the embeddings and seeing how they inform EEG. And the purpose of that eventual PhD is to be using large language models and maybe simpler artificial neural networks as models of the brain and for analogical reasoning. So I don't have any results yet, but he does have a talk coming up at Math Psych. Okay, I'll end there. Thanks for listening.